Hello, my name is Dr. Vincent McNeil, and I'm a system engineer in the High Performance Analog Business Unit in Texas Instruments. Today I'd like to talk to you a little bit about some of the innovations that are driving the development of medical electronics and medical devices. So as many of you know, there are a number of people around the world who have various neurological and neuromuscular conditions that affect them on a day-to-day basis. Now these conditions are often the cause of chemical imbalances or genetic defects or sometimes accidents which affect their ability to walk and move every day. It may be something that manifests itself as a small tremor, or may affect their speech or their gait, or in more grosser or dramatic cases, it may cause them to have involuntary seizures like epileptic seizures or loss of consciousness. Now traditionally, these conditions are treated with pharmacological means such as drugs to treat them and mitigate those conditions. But today I'd like to talk to you about the evolution and innovations in medical electronics and medical devices which allow us to treat those people with those conditions. Now suppose we have someone here, a patient, who's got some kind of neurological condition. And what we'd like to do is chronically implant electrodes into their brain to measure the electrical activity that goes on and hopefully detect whenever they have a seizure or some kind of event going on. Now these electrodes are attached to some kind of low power electronics which amplifies the signal and then perhaps converts it into some kind of digital means. Now it turns out that rather than putting drugs in the body, that we can also treat these patients by applying an imposing force, electrical signal, which basically puts in a current and can cause these electrical storms to quiet down. And typically we apply this with an amplifier and perhaps some data converter. By doing this, we're basically able to remove the tremor or prevent the person from losing consciousness or allow them to regain supple movement in their muscles. And typically what happens, you have some kind of microprocessor or microcontroller in combination maybe with some accelerometers that do the detection, classification, and then apply a therapy to the person, that is the pulse that opposes or provides some current. Now today when we look at these implantable devices, they typically use about 100 microwatts of power. And it turns out that this technology has been borrowed or leveraged from the technology used to treat cardiac patients, those pacemakers or implantable cardioinverters. So you would have a small can which contains the battery and the electronics that runs up the neck and provides signal conditioning path to the electrodes. 100 microwatts of power is what's usually dissipated by the circuit as opposed to 0.5 to 2.5 watts for your typical smartphone today. So the question is, what can we do to drive innovation in this technology? Already today, TI has been looking at taking the voltages required for these circuits down from say 3 volts down to less than 1 volt of operation, which significantly improves the power dissipation in the lifetime of operation. The other thing we're looking at is innovations in terms of miniaturization and novel technology for, say, storage, say the memory that's required to store the information. In our case, we're developing FRAM technology, a non-volatile memory type technology. But how do we take this further? So for instance, suppose you are a patient and your doctor would like to know what's going on with you on a daily basis. How many seizures have you had? How many times have you had to apply therapy? Ideally, we'd like to maybe have a wireless antenna that would basically send their information from the implantable device to your doctor's office. Well, there are a couple problems with this. One is, where does this send it to? And also, sending the information off the body requires a lot of power, which we're trying to save, since we cannot change this battery on a regular basis or recharge like you can with your cell phone. So rather than that, one innovation that's being developed is basically use the body itself as a means of communication. That is, send the information down the hand to something that most of us have every day in our pocket, which is a smartphone or a cell phone. So imagine instead of sending information off the body, that we use the body itself as a communication channel, and then you send the information to your hand, and maybe you have an implantable device in your hand that can talk directly to your cell phone. Today, we already have devices such as NFC, near-field communication devices, which allow you to communicate from your cell phone to a smartphone or a credit card payment system. So you can imagine this information can be sent down the arm to the smartphone. The other advantages besides saving power is that it's secure, so that basically your information is not sent outside, and also can't be hacked by someone who can detect your signal outside the body. So this is how we're making innovations in the area of communications. The other area I'd like to talk about is energy and power management. As I mentioned before, these batteries typically need to last for at least 10 years. Longer is better because otherwise you have to go in and implant or remove the battery and reattach the circuitry. So the body itself is actually generating a lot of energy every day on the order of 10 to 100 watts. And somehow we can scavenge this, recover this energy. We can use it to perhaps power part of this circuitry that's required to detect the seizures. It may not be able to replace the entire battery, but imagine if you were just able to replace the energy required to do the monitoring, which is done on a continual basis, you'll be able to extend the battery life from, say, 10 years to 20 years or 30 years. So that's one goal, is to develop sophisticated energy harvesting, energy scavenging circuitry that can recover some of the energy from the body, whether it's a chemical potential or using motion, and use it to run some of these implantable circuits. The third thing I'd like to talk to you about briefly is the interface itself. Now, it turns out the way that we actually detect electrical signals is that we actually use a potential across the electrode. We measure the difference in potential. Now, the body itself actually does not operate off of electrons, free-flowing electrons, as we do in semiconductors, but in fact operates by movement of charged ions and chemicals. So imagine if you were that instead of trying to put a pulse of electricity into the body to change what's going on, to quiet electrical storm, perhaps we basically created some very small nanoscale MEMS devices that had little reservoirs of chemicals, and chemicals that are neurologically significant, such as L-dopamine. So that when we send a pulse in, rather than stimulating electrically, we're actually triggering a switch here that would cause release of L-dopamine. And that could actually cause the actual therapy effect that we're looking for. In addition, imagine if you had some type of chemical receptor here that could receive L-dopamine or serotonin or some other, again, neurologically important chemical. It could be acetylcholine, et cetera. And that in advance of a big storm or a big event, that could actually detect the chemical imbalance and apply the chemical to the body needed to quiet down and suppress it so that no electricity is required, and we then again save power. The advantage of this is that we now talk about taking this 100 microwatts of operation per day and maybe drive it down to 1 microwatt or even down to the 100 nanowatt type operation. So these are just some of the examples of the innovations that we're working on to drive the medical electronics and medical devices. Now, I've given you an example of a person with, say, Parkinson's disease who has a deep brain stimulation implant, but this can be applied to other conditions. Imagine if you had a spinal cord victim, someone who was injured in a car accident or had a traumatic sports injury or even a warrior coming home. This technology can be used to improve the interface between prosthetic devices or maybe artificial exoskeletons that drive and allow people to walk again. Or we know that there are devices such as cortical implants that help people who have been born deaf or have certain conditions. This would improve the performance of those cortical implants so that people can hear better and more perfectly. Or even people who've been affected by some visual impairment, whether that's macular degeneration or again, some other genetic defects, that this same technology can be applied there as well. So these are some of the innovations that we're working on developing that will affect people around the world with different conditions that give them options on how they can be treated to improve their lifestyle, to improve their ability to live longer and more comfortably, affecting your friends, your family, and the colleagues you work with. So these are just some of the innovations we're working here at TI, and thank you for your time.